So hello everyone, welcome you all to live session 12 of NPTEL course Unitary Operations taught by Professor Shubhita Kumar Majumdar. And my name is Nalfani Sai Kumar. I'm the teaching assistant for this course. So this is going to be our last session for this course. So apart from this, we'll also be having one live session where we'll be covering the entire topics that we have discussed during the course. Okay. So but as per the schedule or as per the lecture that we're discussing, this is going to be the last class. And coming to the extra session will be conducted tomorrow from 10 a.m. to 12 p.m. Okay. So you can ask me any doubts that you might be having throughout the course. So be it any theoretical doubt or anything which is related to basically this particular subject. So if you have any doubts, maybe you can ask me tomorrow. Okay, and I'll try to solve them. Okay. So coming to week 12 course. Okay. So first, we'll have a recap of what we have learned. So last week we discussed about it on week 11. We discussed about measurement of flow. Okay, so we understood what are the different equipments or what are the different classifications that we have in flows like open channel flow or closed channel flow. And then we also studied different equipments which we will be using for measuring these flows. Okay, so we have gone through a variety of instruments for measuring a flow in open channel and closed channel flow. Okay, so we also understood the basics of the flow measurement. So how the science behind the flow measurement. So which parameter is used? Like some cases you'll be using pressure drop, right? So you'll be measuring pressure drop, or basically you'll be applying Bernoulli's theorem. That particular instrument will be using Bernoulli's principle, and based on Bernoulli's principle, it will give us the flow rate of the uh, that particular liquid or gas. Okay, so this week, that is on week 12. We will be studying about multi-phase flow, its phenomena and its applications. So first start, we'll first try to understand what is a multi-phase flow. Then we'll deep dive into the hydrodynamics of a multi-phase flow, and then we'll understand the application of multi-flow as well. Okay, multi-phase flow as well. So coming to introduction, so what do you understand by the term multi-flow or multi-phase flow? What do you understand by the term multi-phase flow? Multi-phase flow. What do you understand by the term multi-phase flow? Anyone? You can type it in the chat box or post them in. You can type it in the chat box or you can unmute yourself and answer me. What do you understand by the term multi-phase flow? So it's nothing but having two different phases in the same flow, right? So be it liquid phase, gas phase, okay, solid phase, liquid phase, something like that. Okay. So if you just go to the proper definition of multi-phase flow, so it is a simultaneous flow of materials with different states or phases. Okay. Let me just write it down. It is a simultaneous flow of materials with different states or phases. Okay, so it could be either a gas phase or liquid phase or a solid phase. Basically, they should be in different phases. Okay, it could also be a simultaneous flow of materials with different chemical properties, but in the same state or phase. Okay, materials with different chemical properties, but in the same state or phase. Okay, so multiphase can be a combination of a liquid phase and a gas phase. Let's start. So we have three phases: right? Solid, liquid, and gas phase. So it could be solid liquid phase. It could also be liquid gas phase. It could also be solid and gas phase, right? But a multiphase flow can be formed with the same phase as well. Okay, so let's take liquid liquid phase. Okay, so we can have a liquid liquid phase. So one could be any oil, and the other could be water. Okay, so if this oil is not miscible in water, then they'll be forming two different phases, right? Like they'll be liquid phases, but they won't be miscible, right? They act as two different entities. Okay, so that could also be a multi-phase flow. So it could be, so this is one example: oil droplets in water. Okay, so that could be an example for multi-phase flow. Liquid liquid, such as oil droplets in water. Okay, so this is best example for multi-phase flow. Okay, so when you're talking about multi-phase flow, there are a few terms that you need to understand. The first one is continuous phase and a discrete phase. Continuous and discrete phases. Okay, so what are continuous phase? What is a continuous phase and what is a discrete phase? So if the flow, or if that particular liquid, say liquid, gas, or solid, if it is flowing continuously, okay, so it is nothing but a continuous phase. And if there are any partitions, okay, like sections, let's say uh, this is a liquid phase, okay, and oil droplets are dispersed in a liquid phase, or liquid flow. Sorry. Then this could be a discrete phase, right? So there'll be gaps between the, or there'll be sections between two different points. Okay, so one phase will be a continuous phase, while the other phase uh, will be dispersed within the continuous phase. So this could be one arrangement of multi-phase flow. One of the phases is continuous, while the others are dispersed within the continuous phase. Okay, so we could be having n number of phases, right? Okay, so let's say we can have a three-phase system. Okay, so multi-phase means you are having more than one phase, right? So you can be having two phases which are flowing simultaneously, or you could also have three phases which are flowing simultaneously, right? Okay, so that is why I wrote others instead of other. Okay, so What could be example? Gas bubble in liquid could be an example. Liquid droplets in gas, continuous gas phase could be example of this, or liquid droplets in another liquid like oil dispersed in water. It could be an example, or solid in liquid or gas phase. That could be an example. Okay, so gas bubbles in liquid. This is a example of continuous phase. Like one phase is gas bubbles in liquid phase is an example of dispersed phase in a continuous phase. So here liquid gas bubbles will be dispersed phase and liquid will be in a continuous phase. And then we have liquid drops in gas phase, in continuous gas phase. And then we have liquid drops in another liquid. Okay. And then we have solid in liquid or gas phase. Okay. So multi-phase flow could be made out of two systems or three systems as well. Okay. First one is gas solid. Then we have gas liquid. Then we have liquid and solid. So on the other hand, we have three-phase flow, that is gas, liquid, and solid. Okay. So these are examples of two-phase flows, whereas these are examples of three-phase flows. Okay. So here gas or liquid acts as a continuous phase, and the discrete phase can be a gas or a liquid, which is acting as a discrete or dispersed phase. Okay. So first, let's see gas-gas system. So can someone give me an example of a gas-gas system? Any example, it could be right or wrong. Examples of gas-gas phase. So so gases can be used as both primary and a secondary fluid. Okay, let's take an example. So how many of you know sulfur hexafluoride, SF6? So SF6 is six times more heavier than air. Okay, six times more heavier than air. So So, so this SF6 can be mixed with argon and it can be used for insulating windows. Used in insulated windows. Okay, this is an example of gas-gas mixture or gas gas-gas system. And then we have SF6, use of SF6 in metal industry. Okay, when casting magnesium, SF6 is used. I'll not be going into the details. I'm just giving you an idea of applications, different applications for gas-gas systems. Used in metal industry for casting magnesium. Okay, and again, eye surgeons use SF6 as a cooling agent in operations. And SF6 is mixed with air, which can be used as a fire extinguishing agent because it is a non-flammable and a cooling gas. SF6 plus air. It can be used as fire extinguishing agent. Okay. Then we have gas liquid flow systems. Can any one of you give me examples of different gas liquid flow systems or applications of a gas flow system? Gas flow system. Where do you use gas flow systems? So, talking in terms of industrial applications, industrial point of view. So, if when gas is a dispersed phase and liquid is a continuous phase, like which is most important to form a multi-phase flow. So, these type of applications or these type of flows are very important in industrial applications. Okay, so you'll understand why in a bit. Okay, so if you look at the applications, okay, or uses of a liquid gas liquid flow systems. So coming to the first example, that is absorption of gases in liquids to remove it from a gaseous mixture. Okay, absorption of gas in liquid to remove it from gaseous mixture. Okay, so one best example is removal of carbon dioxide from polluted air. Okay, so you can also remove many other pollutant gases. So removal of COX NOx is NOx and H2S from polluted air stream. Okay, so you can remove different type of pollutants using a gas liquid system. Okay, gas will be in dispersed phase and liquid will be continuous phase. So I'll give an example. So whenever you want to remove carbon dioxide from any stream, be it industrial stream or removing it from polluted air, you will pass the polluted stream or carbon dioxide rich stream through amine solution, continuous amine solution. So the carbon dioxide which is present in the gas stream, because you know that acidic carbon dioxide is a acidic gas, right? Okay, so whereas amine is a basic solvent. So because of the acid-base attractivity, so amine has more affinity for carbon dioxide basically. So amine will immediately absorb carbon dioxide into the solution. Okay, so when the air, which is initially passed to the amine solution, when it is coming out of the equipment, most of the carbon dioxide would have been captured by the amine solution. Okay, so now we will be left with carbon dioxide free air stream. Okay, so that is how you'll be able to remove. This can be done for other gases as well. You just have to change maybe solvent. Okay, but you can do it for other gases as well. So you'll be able to remove the unnecessary gas from the gas stream. Okay, and other examples of gas liquid systems are ozonization of arsenic or ammonia or dye for water treatment. Ozonation of arsenic or ammonia or dye for water treatment. Okay. This is also basically removal of all the substances. And then we have a distillation process. Distillation process is also sorry, example of gas liquid system. And then we have gas liquid chromatography, which basically works on the same principle for analyzing liquid petroleum products. Application of gas liquid chromatography to analyze or for analysis of liquid petroleum fractions. Okay, so this is one more application of gas liquid systems. And then we have gas liquid reactions, which basically occur in industries like uh, reaction between whenever we are producing chemicals using synthetic methods. Again, this gas liquid phase will be useful. Gas liquid reactions. Industrial gases like O2, H2, that is oxygen, hydrogen, carbon monoxide, sorry, and carbon dioxide. They are widely used for synthetic process in chemical industry. So there also will be coming across this gas liquid flows or gas liquid systems. Okay. Then we have gas solid system. So for a gas solid system, most of the applications, solid will be suspended in gas stream. Okay. Sorry. So coming to applications, one is a physical process. Or in other words, we can say there will be no reactions happening in the system. Okay. So what are the examples of physical processes for gas liquid, sorry, gas solid systems? Drying of particles is an example of gas liquid systems. Coating of a surface is an example of gas solid systems. Then we have granulation, which is growing particles. Okay, and then we have heat treatment. Heat treatment is also sorry, heat treatments like annealing, quenching, filtration. Filtration also gas like solid operation. Then we have blending, classifications. These are all examples of gas liquid systems where there will be no reaction or it's a pure physical process. Drying of particles, coating of surfaces, granulation, heat treatment, filtration, blending, and classification. And on the other hand, we have chemical reactions. So gas, solid reactions. It could be roasting of ores. Okay, so it's nothing but heating them to higher temperatures in the presence of oxygen. Okay, so it is converting them, roasting of ZNS, Cu2s, that is, and then we have nickel sulfide, nickel sulfides. Okay, so these are all examples of gas liquid systems. Then we have combustion and incineration. We also have gasification, coking, pyrolysis, calcination, carbonization. Okay, so all these are examples of gas solid reactions. Then we also have catalytic regeneration, fluorination of uranium particles. Okay, so if you can add any chemical reaction, okay, which is basically supported by a catalyst and occurs in the gaseous system, you can add into these examples. Okay, like fluid coking, reduction of iron oxide, all these examples would come under gas solid reactions. Okay, so what would be the next system? We are done with gas, gas phase, right? Like gas phase in combination of liquid and solid. So what will be the other example? Or what will be the next example? What will be the next case? So that would be liquid, liquid or liquid solid. Okay, so first let's see a liquid liquid system. Liquid liquid system. Okay, so liquids are used both as a discrete and a continuous phase. Okay, so applications would be emulsification of oil, used for flow of emulsion of oil and water in pipelines. And then we have a different type of contactors like packed columns, pulsated columns, and sealed reactors. Okay, in various applications. And then also extraction of organic contaminants from wastewater. Okay. And as I've told you, there are many different type of contactors like packed columns, pulsated columns, stir tanks. So all the reactions are happening in these columns. They'll again fall in the same category as liquid-liquid systems. Okay. And then we have liquid solid systems. So finally, we have liquid solid systems. This is the last classification in a two-phase system. Okay. Then we have three-phase system again. Okay. So again, here liquid is going to be a continuous phase and solid is going to be a discrete phase. So what could be the examples of this type of systems? Sorry. What could be examples of a liquid solid system? Any one example? Okay. So we know conveyors, right, where they'll be transporting solid matter from one location to other location. There's also something called hydraulic convey, where they'll be using a liquid for transporting. First, they'll be mixing solid in gaseous phase, or they'll be dispersing solid in gaseous phase, sorry, liquid phase, and then they'll be transporting the solids from one place to another place with the help of the liquids. Hydraulic conveying of solid materials. Then we have slurry flow applications, which basically includes transportation of coals, ores, okay, and also flow of mud. These are all examples of liquid solid systems, okay. And then we also have crystallization process. Crystallization process again, solids will be suspended in liquid phase, right? Crystallization of solids. And then we have flow of liquids through solids, which is also an example of uh, liquid solid system. And this is a porous media flow. Okay. So we are done with two-phase systems. Now let's also study multi-phase flow, three-phase system. Okay. First one is gas, liquid, solid system. Okay. So gas, liquid, solid system. Basically, gas liquid reactions happen in the presence of a solid catalyst. Okay. Okay. Then we have let's say A and B are reacting to give some product C, okay? And then we have a solid catalyst. Okay, A could be in a gaseous phase and B could be a liquid phase. Okay, so this is again a gas liquid solid system, right? Sorry. So this is an example of a gas liquid solid system, and then we have gas liquid liquid system. This is also an example of three phase systems. Okay, examples could be oil, water, and natural gas, which is found basically in the condensation or evaporation of immiscible liquid mixtures. Okay, flow of oil, water, and natural gas. So here, water and oil are in liquid phase, and natural gas is in solid phase. Okay. Then we have solid liquid liquid systems, solid liquid and liquid systems. So in a pipeline, if sand is mixed with oil and water, then this flow comes in a solid liquid liquid systems. Okay. So these are three different three phase systems, and then we finally have a four phase system as well. So this is liquid, liquid, gas, solid system. Okay. In a freeze desalination process, when butane liquid is added into saline water, which results in the formation of icils. So in this case, the system is a mixture of butane liquid, water, ice, and a butane vapor. Okay. So this is basically liquid, liquid, gas, solid. So liquid is water, and then we have butane liquid, gas is butane vapor, and solid is ice. Okay. So this freeze desalination process. So why do we need to learn a multi-phase flow? Okay. So this will be helpful in proper design of efficient multi-phase units. Okay. So as I've told you, most of the industrial operations, they are based on a multi-phase flow. Okay. So understanding a multi-phase flow will help you in better designing of the process. Okay. Which results in efficiency and economical advantage for the industry and also for the company as well. Okay. So you need to understand hydrodynamic parameters. Okay. So it is like flow regime, phase fractions, and also you need to understand fractional pressure drops, then also friction factors, particle or particle bubble interactions, particle droplet interactions. You need to understand turbulence and flow structure, and then mixing of a multi-phase flow. Okay, distribution mechanism of each phase, and this will help you in understanding scale-up issues like increasing the bed diameter, particle size, what happens when you change the arrangements of heat exchangers, mechanical arrangements of heat exchangers, and also when you change L by D ratio, what is going to happen. So this helps you in addressing all these problems. Then you can also better understand heat transfer characteristics, mass transfer characteristics, and also you'll be able to simulate the system better. Okay. So let's just recall a single phase flow. So whenever it is flowing in a pipe, when RE is greater than 4000, that is a turbulent flow, right? So whenever you're injecting a dye, whenever the flow is highly turbulent, and when you're injecting a dye to this stream, you can clearly see that there is rapid mixing happening in the stream. Okay, so this is unpredictable, and also rapid mixing happens, right? Then we have RE. Then we have a situation where RE is less than is in between 2300 to 4000. This is a transitional flow, and same thing. If you inject a dye into this particular system, you can see there is turbulent outburst in the flow, and then you have finally the laminar case when RE is less than 2300. Okay, this is a predictable and slow mixing flow, right? So basically, when you're increasing the velocity, sorry. So this is about single phase flow. Okay, so but what happens when you change different parameters for, or what would be the flow regime for, or flow pattern for a multi-phase flow so in a gas, so let's take an example of gas liquid flow. Okay, so when a gas and a liquid are forced to flow together inside a pipe, there are at least seven different geometrical configurations at different stage of operations. So these multi-phase flow behaviors can be affected by different parameters. Okay, are affected by interfacial tension forces. I'll just write down these parameters. Interfacial tension forces, weighting characteristics of weighting characteristics of the liquid on the channel wall, contact angle, and finally exchange of mass, momentum, energy between the different phases. Exchange of mass, momentum, and energy between different phases. Okay, so these are the different parameters which are going to affect the flow of a multi-phase flow. So we have let's first start with horizontal concurrent gas liquid flow patterns. Horizontal concurrent gas liquid flow patterns. First we have stratified flow. So stratified flow is usually observed at relative low flow rates of gas and liquids when gravitational separation is complete. So the liquid has a tendency to occupy the lowest part because of obviously density issues. So liquid has a tendency to occupy the lower part of the tube, whereas gas occupies the top part of the tube and is separated by a undisturbed horizontal interface. So this looks something like this. So let's say if we have a pipe and gas and liquids are flowing in this, you can clearly see a line which is separating. So this is going to be the liquid phase and this is going to be gaseous phase. Okay. And then we have stratified wavy flow. Stratified wavy flow. So as the gas velocity increased, waves started to will be starting to form at the gas liquid interface, and which results in a wavy or stratified wavy pattern. So if you increase the velocity of or speed of the gas flow, then you'll observe these waves which are being formed inside the gas liquid system. And the amplitude of waves depends on the relative velocity of the two phases. Okay, this is the second fluid is stratified flow. And then we have bubble flow. So this in this particular system, the phase is composed of bubbles dispersed in a liquid stream, and the bubbles tend to accumulate in the upper part of the tube because of buoyancy forces. And the uniform distribution of bubbles occur when there is a domination of shear forces on the bubble surface, and the pattern typically occurs at high mass flow rates. Okay, so liquid will be condensed phase and bubbles will be dispersed in the phase, and at higher flow rates, this occurs at higher flow rates, and basically these bubbles they'll be seen in the top section of the pipe, okay, and the upper side of the pipe because of the buoyancy forces. And then we have annular dispersed flow. When you further increase the gas flow rate alone, okay, so without changing flow rate of liquid, if you increase the gas flow rate, the liquid forms a continuous annular film around the perimeter of the tube. And the pattern is similar to that in a vertical flow as well, except that the liquid pattern tends to be a much thicker at the bottom than the top because of the gravitational force. And a portion of the liquid may be retained as a fine droplets within the gas core. Okay, so liquid will be at the edges. Okay, so this will be liquid phase, and here you can see the gas that is flowing. Okay, so basically liquid will be forming a angular flow and gas will be flowing in between the in this section. Okay, Then we have plug flow. In this flow pattern, liquid plugs are separated by elongated gas bubbles, which tend to flow along the top side of the tube due to the buoyancy forces. As the gas flow rate is increased, bubbles interact and close to give rise to a larger bullet shaped bubbles. So blood flow is sometimes referred to as elongated bubbly flow as well. So basically, liquid will be separated because will be separated by gas bubbles, something like this. You can see plugs which are being formed. Okay, and then we have slug flow. In this case, a frothy liquid slug is formed at the higher gas velocities, and the crest of the waves touch the top of the tube, and the frothy slugs of the liquid phase carries entrained bubbles in it. The slug completely fills the cross section of the tube, and the main characteristic between a slug flow and a plug flow is in more pronounced nature of the intermittent liquid mass separated by a larger gas bubbles. And these slugs can be often be very big and may cause some serious difficulties in the operation of horizontal pipes. So let me just show you how this look like. Same, it's almost similar to the plug flow, but the thing is, the intermittent liquid mass separation will be separated by a larger by larger gas bubbles. Okay, so this is how it looks. This will be liquid phase, and here you can also see some gas bubbles which are entrained, and this is gas phase. Okay. Sorry. And then we have mist phase or mist flow. So at very high mass fluxes, the under flow becomes thinner by means of a shear of gas core, and because of this, interface will become unstable. And when it becomes unstable, all the liquid is entrained as droplets in the core gas region. The droplets are too small that it consequence the flow as a mist flow. The fine droplets immediately wet the tube wall. So if you just take the example of annular flow which we discussed and increase the flow rate of gas inside it. If you go to very high mass fluxes, then the liquid which is present at the edge of this pipe, they'll be they'll become unstable and the liquid will be entrained as droplets in the core gas. So here liquids will be dispersed in the liquid droplets, fine liquid droplets will be dispersed in the gas stream. Okay, so this is how mist flow looks like. So these are different type of flows in gas liquid streams, co-current gas liquid streams in a horizontal pipe. Then we also have the case of vertical flow or vertical pipeline flows. So how does this vary in a vertical flow? So obviously, gravitational force will also start acting when you're dealing with vertical pipeline, right? So you need to take that into account, and also flow behavior will be changing a little bit. So I'll not be going into that part, okay? So which was already discussed in the class, so I'm not going to into that. I'll try to take the next chapter. So which factors depend flow pattern, okay? Or which flow pattern depends on which type of or which parameters. Flow patterns depends on what, which is going to affect the flow pattern, or which parameter is responsible for the flow pattern. The flow pattern of a multi-phase flow is a in a context depends upon several factors like dynamic variables. It also depends upon geometric variables. It depends on thermodynamic variables and also physical properties of the phase as well. So let's try to look at each parameter. So first is a dynamic variable or dynamic variables. So what are the dynamic variables that are affecting the flow pattern? So we have flow rate of the phases, phase fractions. So these are the dynamic parameters. Then we have geometric variables. Okay, like diameter, length, shape of inclination of conduct, particle size, hole size of a phase, distributor. Okay, walls, T junctions. These are all different geometric variables which are going to affect the flow pattern. So diameter, length, shape, etc. Okay. Then we have thermodynamic variables. So like pressure, temperature, adiabatic or diabatic conditions. So these are thermodynamic parameters which are going to affect the flow pattern. Pressure, temperature, etc. And then we have physical properties of the fluid. Physical properties, and the phases like density, surface tension, viscosity, etc. So these are different parameters which are going to affect the flow pattern. Okay, so do you have any doubts until now? Any doubts till this topic? You can post them in the chat box or until your friend ask me. Any doubts? If you don't have any doubts, I'll move on to the next topic, that is flow map. So the graphical representation of boundaries or transitions between different flow patterns is called a flow pattern map. We'll also look at example of a flow pattern map. First, let me write down the definition. The graphical representation of boundaries or transitions between different flow patterns is called flow pattern map. Okay. A set of parameters or parameter groups are specified to show a direct interrelation on such transitions based on the experimental data. And we'll also look at a flow map in a horizontal pipe as well. Flow pattern map in horizontal pipe. There is a graph between superficial liquid velocity, superficial liquid velocity, which is in meters per second, and then you have on x-axis superficial gas velocity. This is again meter per second. So I can write down the units as well. This one is 10, 100.1. This is wave flow, annular or annular mist flow. Then we have dispersed flow. This is slug flow. Bubble or elongated flow. Is stratified flow. Okay. So when you increase superficial gas velocity, okay, let's say initially gas is flowing at 1 meter per second, and liquid flow rate is or liquid velocity is below zero point 0.1 meter per second. So we'll be initially having a stratified flow. But if you increase superficial gas velocity from 1 to 10, okay, keeping flow rate of liquid constant, then we'll be moving from stratified flow to wavy flow, okay, because of the friction force between gas flow and the interface. The gas flow will start to move the interface as well. Okay, so this was the second type of flow that we discussed, right? So you'll see that the interface is disturbed and it will be in the form of waves. Okay, initially the separation between liquid phase and gas phase in the stratified flow will be a perfect horizontal line. But as you increase the flow rate of gas velocity, you will see that the interface is disturbed and it will be in the form of waves. And if you further increase the flow rate of gas phase beyond 10, around 80 or 90, then you'll see that the flow has been changed to annular flow. Okay, so gas will be flowing in at the center of the pipe and liquid will be at the walls. And if you further increase the velocity, then you can also see mist flow as well, which is basically liquid getting dispersed in gas phase. Okay, but when you come to the initial condition where liquid is at zero point 0.1 meter per second and the gas is flowing at 1 meter per second. So keeping this coming to this condition again. So let's say from here, if you have placed gas velocity constant and increase the liquid velocity to let's say 1 meter per second, Then the flow rate changes from stratified flow to bubble flow or elongated bubble flow as well, depending upon the velocity regime of the liquid. Okay. And if you further increase it, then it can also be changed to dispersed flow, where gas bubbles will be completely dispersed in the liquid phase. Okay. And then we also have slug flow, which is like intermediate. You can have slug flow when liquid is having an average velocity, like intermediate velocity between zero point 0.1 to 100, like let's say around close to 10, not middle value. So it could be ranging from 1 meter per second all the way to 15 meter per second. And this is for gas phase. And for liquid phase, it could be for liquid phase, it could be anywhere between from zero point 0.1 to slightly above 1. Okay. So this is how the flow rate changes. That is how you draw a flow map for liquid phase and depending upon the liquid and gas phase velocities. Okay. So you can do it for vertical pipe as well. This is for horizontal pipe. You can do the same thing for vertical pipe as well. Okay. So now let's look at volume fractions or hold up of phases. Volume fraction or hold up of phase. Okay. So the volume fraction of a dispersed phase can be defined as alpha D, which is nothing but VD by V total. Okay. This can also be written as AD by A. Okay. So VD is a volume of dispersed space and VT is the total volume. And the volume of or volume fraction of continuous phase can be written as VC by VT, which is continuous phase volume upon total volume. This can also be written as AC by A. Okay. So where VD is again same dispersed phase volume and VC is the volume of continuous phase and total volume is VD plus VC. VT is equal to VC plus VD. Okay. So the reason for writing AD instead of VD is that, so let's take alpha D, that is volume fraction of dispersed phase. So what is alpha D? That is VD by VT, right? So volume can also be written as area into length, right? And same for total velocity, for total volume, we can write total area into length, right? So here length is constant. It is not going to change. So this finally becomes AD by A. Similarly, here you can just write it as AC into L by A into L. So length gets cancelled out and you'll be left with AC by A. Okay. So now let's see how to calculate gas hold up and liquid hold up. So let's consider a gas liquid two-phase flow. Gas liquid two-phase flow. So let's say gas is dispersed and liquid is continuous. Okay. So gas hold up can be written as is alpha G can be written as alpha G is equal to volume of gas by volume of gas plus volume of liquid, which is equal to Vg by Vg plus VL, right? And same for liquid phase, liquid hold up, alpha L will be volume of liquid by volume of gas plus volume of liquid. Okay, so this is going to be VL by Vg plus VL. Okay, so if you just carefully observe, if you add up alpha G and alpha L, what will be the value of this? It is going to give us 1, right? This is nothing but volume fractions or mole fractions. Okay, so and alpha G plus alpha L will be equal to 1. Okay, let's say in a situation A is constant and L is changing. Okay, so that means alpha D is actually there is a formula for alpha D, or let's say alpha G Vg by Vg plus VL, right? This can also be written as Vg by Vt, which is nothing but A G by AT, right? But let's say this is only possible if L is constant and A is changing, right? But let's say if A is constant and L is changing, how do you write in this case? So alpha G will be equal to Vg by Vg plus VL, and this can be replaced with A Lm or A Lg. I think we have to take an example for this. It would be better if I take an example. Or first, let's cover one more topic and then we'll come back to this. Okay, bulk density. Bulk density. Okay. So what is bulk density? Bulk density of dispersed phase is the mass of dispersed phase per unit volume of mixture. Okay, rho d, that is bulk density of dispersed phase will be equal to mass of dispersed phase upon total volume, that is Vt. Okay, and then we have material density as well. Okay, it is rho d and alpha d, sorry, rho d bar can be related to rho d by multiplying this with alpha d. So this gives us particle density. This is how you'll be able to calculate particle density using bulk density of the phase. Okay. The sum of bulk densities for dispersed phase and continuous phase is the mixed density. So alpha d bar plus, sorry, rho d bar plus rho c bar, that is continuous phase bulk density, will be equal to rho m, that is mass of sorry, density of mixture. So we can also write this as rho m is equal to rho g bar plus rho l bar. Okay, which can be written as alpha g into rho g plus 1 minus alpha g into rho L. Okay, because for the gas liquid systems, alpha g plus alpha L is equal to 1, right? So using this, we can write rho L as alpha L as 1 minus alpha g. Okay. Then how do you calculate viscosity of a mixture of multiphase flow? Viscosity of the mixture of multiphase flow. Okay. So 1 by mu m, that is for mixture, will be equal to x by mu g. plus 1 minus x by mu I. Okay, I'll not be going into the derivation part. And mu g is viscosity of gas, and mu L is viscosity of liquid. So here x is the mass quality of dispersed phase. So which is equal to rho g bar by rho m bar. Okay, this will be equal to alpha g into rho g by alpha g into rho g plus 1 minus alpha g into rho L. Okay. So do you have any doubts until now? Any doubts till now? If you have any doubts, you can unmute yourself and ask me or post them in the chat box as well. I'll give you maybe 1 2 minutes. If you have any doubts, you can ask me. I'll try to answer them. Please post them in the chat box or directly ask them by unmuting yourself. Okay. So I'm assuming that you don't have any doubts. So we'll move on to the next topic, that is superficial and interfacial velocities. Superficial and interstitial velocities. For a multi-phase flow in a pipeline, the superficial velocity of each phase is the mass flow rate of that phase divided by the pipe cross-section area, that is A, and a material density. So the superficial velocity can be written as U SD. SD indicates superficial, and this will be equal to m dot, that is mass flow rate, divided by area of cross section into density. Okay. So this is for superficial. This is the superficial velocity of dispersed phase. That is why D, and S indicates superficial. Okay. In other words, it is a velocity of phase if the phase occupied the whole pipe cross section or entire pipe cross section. If it occupies the entire cross section. This is going to be the density of that particular, oh sorry, velocity of that particular phase. And the phase velocity u id, that is intrinsic or actual velocity of the pipe, the phase. So if it is sorry, if uid is the intrinsic or actual velocity of the phase, then superficial and interstitial velocity are related by volume fractions as USD is equal to alpha d into UID. Okay, so here UID can also be written as QD by AD, which is equal to USD into A by AD. So this becomes alpha. So here we'll be getting USD into, sorry, by alpha, USD into alpha, USD by alpha D. So if you just simplify this, you will be getting this equation. Okay, so this is how superficial velocity and interstitial velocity are related. Okay, then we have slip or relative velocity. So the relative velocity between two phases, such as gas and liquid phase, in case of a two-phase flow, is denoted by UR, comma G dash L. Okay, so it is denoted by UR, comma G dash L. That is relative velocity between gas phase and liquid phase. So this can be written as UIG plus UIL, which is again equal to USG by alpha G plus or minus USL by 1 minus alpha G. Okay, this is nothing but alpha L. As is a two-phase flow, we can write alpha L as 1 minus alpha G. Okay, positive sign indicates it is a counter current flow, and the negative sign indicates that it is a co-current flow. And the relative velocity is sometimes referred to as slip velocity as well. Okay, and then we have frictional pressure drop. Frictional pressure drop. So pressure is one of our main design variable, right? So it governs the flow energy required to transport multiphase flow in a certain flow systems. So the multiphase flow in a pipe is rendered more complex phenomena where movement of phases constitute several changes in flow behavior to influence the transport processes in the pipe, either the discretion of flow in a vertical or horizontal. And the flow practice is to multiply the single phase pressure losses by a factor known as two phase multiplier, which is empirically correlated. And the pressure head or head loss which occurs in all piping systems because of elevation changes, turbulence caused by abrupt changes in directions, and friction within the pipe fittings. So basically, delta PT will be equal to delta PS plus delta P mom plus delta PF. Okay. So here delta PT is the total pressure drop. Okay. And when delta PS is the hydraulic pressure change. So the pressure changes which occur due to the difference in height. Sorry, hydrostatic is not hydraulic, hydrostatic. So the pressure changes due to hydraulic, sorry, sorry. So the pressure changes due to difference in heights is known as hydrostatic pressure difference. And hydrostatic pressure head, this term is based on the true average density of a mixture in the pipeline, which is evaluated with a precise knowledge of the holdup of liquid and gas in a pipe section. And P momentum, this is calculated when the pressure different phases do not have the same velocity, which is causing a change in momentum and thus pressure drop as well. So that will contribute to delta P mom. And then we have delta PF, which is because of friction, the friction between two phases and between the phases and the wall, column wall contribute to this delta PF. Okay. So there are different formulas to calculate the frictional pressures. I'm not going into that, which we'll already discussed in the class. So we'll go to the next topic is phase interaction. First, let me write this down. For gas liquid two-phase flow, we have bubble coalescence, bubble breakup, bubble size distribution. And for liquid flow, droplet breakup, its size distribution. Okay. And for gas liquid three-phase flow, just a second. For the gas liquid three-phase flow is bubble solid, and liquid solid interactions. Okay. So I think we are running out of time. So if you have any doubts in the entire week 12 class, you can ask me. I'll try to answer them. As we're running out of time, if you don't have doubts, I'll move on to the problems part. Any doubts until now? Any doubts until now? Any topic? If you don't have any doubts, and we can move on to the problems part. If you have any, you can unmute yourself and ask me, or post them in the chat box as well. Any doubts till now? If you don't have any doubts, let's move on to the problem solving part. Coming to the first question, multi-phase flow is a simultaneous flow of option A materials with different states or phases. Option B materials with different chemical properties but same state or phase. Option C both A and B. Option D none of the above. So multi-phase flow is a simultaneous flow of materials with different states or phases. Okay, and then we also have one more definition that is flow of materials with different chemical properties but in the same state or phase. This is also an example definition of multi-phase flow. So that will be option C, both A and B. Coming to second question, roasting of ores is an example of what type of multi-phase flow? Gas flow, gas solid phase, gas solid flow, gas liquid flow, solid liquid flow, none of the above. So roasting of ores is an example of gas solid flow. That is option A, right? Coming to third question, performance of a multi-phase unit is determined by which of the following? Option A, design variables. Option B, kinetic and thermodynamic variables. Option C, process operating variables. Option D, all the above. Which of the parameters or variables will affect the performance of a multi-phase unit? That would be option D, all the above, right? Coming to fourth question, in a spray column, the liquid is a discrete phase while gas is the continuous phase. This configuration is beneficial for separating gases pollutants that are option A partially soluble in liquid, option B highly soluble in liquid, option C reactive with liquid medium, option D none of the above. So this will be helpful when they are highly soluble in liquid. That is option B. Okay. So coming to fifth question, pipeline drilling involves which kind of multi-phase flow? Option A, liquid solid. Option B, solid gas. Option C, gas liquid solid. Option D, gas liquid liquid. Pipeline drilling will involve gas, liquid, and solid flow systems. That is option C. Okay. So coming to sixth question, multi-phase flow behavior are affected by option A, interfacial tension forces. Option B, contact angle and weighting characteristics of the liquid on the channel wall. Option C, the exchange of mass, momentum, and energy between the phases. Option D, all the above. And be option D, all the above. Okay. So that is it. If you have any doubts in either the theory part or the problem section, you can unmute yourself and ask me or post them in the chat box as well. This is going to be the last session. That is week 12. After this, we don't have any other syllabus to cover, but we do have one more session tomorrow from 10 a.m. to 12 p.m. where we are going to have recap of what we have learned until now. Okay. And if you have any doubts as well, I'll try to answer them tomorrow. So, any doubts in this session? Sorry. So, I'll keep this session open for a few minutes. Google Meet. If you have any doubts, you can ask me. I'll be here or post them in the chat box as well. I'll try to answer them. If not, others can leave the session. So thank you everyone. Thank you for attending the session. Let's meet tomorrow for one final session to have a recap of what we have learned until now. And if you have doubts as well, I'll try to answer them. Okay. So the timing is from 10 a.m. to 12 p.m. tomorrow. Okay. So thank you everyone. Thank you for attending the session.